U.S. Quantum Initiatives. Executive Summary. The U.S. government invests heavily in quantum technologies, computing, sensing, and communications because they promise major advances in security, science, and industry. Agencies like DARPA, NSF, DOE, and NIST lead programs to accelerate research, build infrastructure, and train a skilled workforce. DARPA's Quantum Benchmarking Initiative tests which technologies can achieve useful, scalable performance. The National Quantum Initiative coordinates nationwide efforts supported by legislation like the CHIPS and Science Act. Despite challenges in scaling, coordination, and talent shortages, federal funding, over $1 billion annually, aims to keep the U.S. competitive as quantum systems evolve from lab experiments to real-world applications. Article Why the U.S. government invests in quantum technology. Quantum technologies, like quantum computing, quantum sensing, and quantum communications, are at the frontier of modern science. Together, these fields are known as quantum information science, QIS. They promise to revolutionize computing power, communication security, sensing precision, and materials research. Because of their potential to shape national security, the economy, and future industries, the U.S. government has made major investments to accelerate quantum research and development. Why quantum matters? There are four main reasons the federal government is pushing quantum innovation. 1. National security and defense. Quantum sensors could help navigation in places where GPS doesn't work. Quantum communications may allow unbreakable encryption. Quantum computers could also be used to test the limits of cryptography and security systems. 2. Global competitiveness. Quantum is expected to be a foundational technology, much like semiconductors and the internet were. Staying ahead in quantum research helps the U.S. avoid falling behind other countries such as China or members of the European Union. 3. Scientific and industrial progress. Quantum tools could speed up discoveries in chemistry, energy, medicine, and materials science, helping industries design better batteries, drugs, and superconductors. 4. Workforce and infrastructure. Quantum progress requires trained scientists, engineers, and advanced lab facilities. The government wants to build a strong national ecosystem for this field. With those goals in mind, several U.S. agencies, especially DARPA, have launched large-scale programs to drive quantum research forward. DARPA's role in quantum innovation. The Defense Advanced Research Projects Agency, DARPA, has always focused on high-risk, high-reward science. It helped create the internet, GPS, and stealth technology. Now it's playing a key role in quantum innovation, trying to move discoveries from the lab into real-world prototypes. Early programs. QUIST, Quantum Information Science and Technology, 2001 to 2005. This was one of the first major U.S. efforts in quantum computing, communications, and algorithms. A major result was the DARPA Quantum Network, a real-world test of quantum key distribution, QKD, that linked sites around Boston and Cambridge through fiber optics. It proved that secure quantum communication could work outside the lab. QUEST, Quantum Entanglement Science and Technology, started in 2008. Building on QIST, QEST explored entanglement, quantum algorithms, and new sensing methods. These early efforts laid the foundation for future research. While these programs were groundbreaking for their time, their scope was smaller than today's national ambitions, modern and ongoing initiatives. In the last few years, DARPA has shifted focus toward benchmarking and validation, testing which approaches to quantum computing can realistically achieve utility scale. These would be systems powerful enough to provide practical value. Quantum Benchmarking Initiative, QBI. QBI's goal is to see if it's possible to build a useful quantum computer by 2033. faster than most experts expect. The program measures performance, cost, and reliability to determine which designs can truly outperform classical computers. QBI builds on earlier DARPA programs, such as US2QC, underexplored systems for utility-scale quantum computing. Companies like Microsoft, IonQ, PSI Quantum, and SEEQC are participating, submitting system designs for independent evaluation. The most promising designs will move to later, better-funded stages. Quantum sensing and navigation. Beyond computing, DARPA funds research in quantum sensing and positioning, navigation, and timing P and T systems. These could allow precise navigation where GPS is unavailable, a major defense advantage, partnerships, and hubs. DARPA collaborates with universities, companies, and state governments. One example is the Capital Quantum Benchmarking Hub in Maryland, developed with the University of Maryland. Projects under QBY often pair private companies to combine different technical strengths. Overall, DARPA's current approach is to test, compare, and validate multiple technologies to find which ones can scale into reliable quantum systems. Other U.S. federal quantum efforts. DARPA is just one part of a larger national effort. Many federal agencies coordinate under the National Quantum Initiative, NQI, which organizes funding, research, and workforce training. The National Quantum Initiative, NQI, Congress passed the National Quantum Initiative Act in 2018 to create a unified national strategy. The Office of Science and Technology Policy, OSTP, and Quantum.gov coordinate these activities. Under the NQI, agencies like the NSF, DOE, and NIST align their programs, share data, and report progress through the National Science and Technology Council's Quantum Subcommittee. The Act also supports national research centers and public-private partnerships. National Science Foundation, NSF. The NSF funds basic quantum science at universities. It backs projects in computing, communications, materials, and sensing. Notable programs include the National Quantum Virtual Laboratory, NQVL, which builds shared infrastructure for quantum research nationwide. Expand QISE, a $39 million program to help more universities participate in quantum research and education. Department of Energy, DOE. The DOE leads large-scale efforts through its national labs. It funds 5 national quantum information science research centers, NQISRCS. They have invested over $575 million to unite labs, universities, and companies. DOE also funds hardware testbeds like QSCOUT at Sandia National Labs, where scientists can access real quantum hardware for experiments. National Institute of Standards and Technology, NIST. NIST focuses on standards and measurement, crucial for accurate quantum devices. It develops quantum clocks, error correction benchmarks, and communication protocols. NIST often partners with other agencies through the NQI network. Department of Defense and Intelligence agencies. Outside DARPA, other defense branches, the Air Force, Army, and Navy all have quantum projects in sensing and communication. The NSA studies post-quantum cryptography, preparing for a future when quantum computers could break today's encryption. However, the NSA has warned that QKD, quantum key distribution, isn't yet ready for national security use. Legislation and policy support. Major federal laws and budgets also support quantum growth. The CHIPS and Science Act 2022 funds research, workforce training, and infrastructure related to quantum and semiconductors. New bills have proposed billions more for quantum R&D. The U.S. currently spends over $1 billion per year across all agencies on quantum programs. A recurring theme is workforce development, training thousands of new quantum engineers, scientists, and technicians for both research and industry roles. Challenges and strategic issues. Despite huge momentum, the U.S. quantum effort faces several key challenges. 1. Measuring true utility. Passing performance benchmarks doesn't always mean a system is practical. Real-world scalability, error correction, and cost remain difficult hurdles. 2. Balancing resources. Policymakers must decide how much to fund basic science versus hardware prototypes or near-term applications. 3. Coordination. Many agencies fund quantum work. The NQI tries to keep them aligned, but overlapping missions and bureaucracy can slow progress. 4th, international competition. China, the EU, and others are investing heavily. Securing supply chains for specialized quantum hardware is now a strategic priority. 5. Workforce shortage. There aren't enough trained quantum professionals. Education and retraining programs are critical to meet growing demand. 6th, deployment challenges. Many quantum systems only work under lab conditions. Turning them into reliable, deployable tools for defense or industry will take years of engineering. Outlook: the next decade. The U.S. government's investment in quantum is both scientific and strategic. DARPA remains central, focusing on benchmarking, competition, and validation through programs like QBI and US-2QC. Other agencies, NSF, DOE, NIST, and the broader National Quantum Initiative, provide the foundation for basic research, testbeds, and workforce development. Laws such as the CHIPS and Science Act and proposed new funding packages show continued bipartisan support for quantum progress. While big challenges remain, from coordination to scaling hardware, momentum is strong. Over the next decade, quantum technology will likely move beyond lab demonstrations into practical uses, especially in sensing and communications. Quantum computing may take longer, but it holds the potential to transform science, defense, and industry for decades to come.